Assalamu alaikum. My name is Dubna Batul, MS Chemistry, Batch 7. Today, the topic of my presentation is Chemical Vapor Deposition Technique Application in Graphene Based Products. So, in this topic, I will discuss what is graphene, its introduction, properties of graphene, and then we will see its synthesis method, that how can we synthesize a graphene. It include mainly two types, top down and bottom up techniques. Then we will discuss that how can we prepare a functionalized graphene, what methods we will use and prepare a functionalized graphene. Then we will see a chemical vapor deposition method, which is mostly used to prepare graphene. And then we will also see plasma chemical vapor deposition method. And then we will discuss graphene properties, its application, which we will see in transistors and transparent displays, coating, biomedicine, agriculture, waste management, and in anti-cancer, and in also many other fields. And at last, we will discuss its conclusion and its future prospect, that how in future we will use graphene in our daily based products. So now let's start our topic. So what is graphene? Graphene is basically sp2 hybridized structure with two carbon atoms in a unit cell. This SLG stands for single layer graphene. So this is sp2 hybridized structure which have two carbon atom in a unit cell. So these two carbon atoms are located in A and B position respectively, which we will see in figure. BLG. Now what is this BLG? BLG is basically Bernal stacked bilayer graphene, and this is a flexible material with tunable band structure. Tunable means that its band structure is flexible. So this mainly possesses two different characteristics. One is its tunable band gap, and second one is gapless metallic bond. Tunable band gap is basically induced by large displacement field, and gapless metallic bond occurs at low field with a rich fine structure. So this Bernal layer so this Bernal stacked bilayer graphene can be basically primarily divided into three categories: AA stacked, AB stacked, and twisted. On the other hand, TLG trilayer graphene has three stacking positions: the AAA, ABA, and ABC stacking positions. These represents the hexagonal, Bernal, and rhombohedral arrangements, which we will see in our figure. 3 out of 4 valence electrons for each carbon atom in graphene honeycomb lattice overlap with the adjacent carbon atoms. As we all know that there are 4 electrons in the valence shells of carbon. So 3 valence electrons for each carbon atom in a graphene form a honeycomb-like lattice with the adjacent carbon atom within a sheet and forming a strong sigma bond. The exceptional flexibility of graphene lattice structure is due to this sigma bond. The remaining fourth electron, the fourth one which is left, in the pz orbital overlap with the neighboring orbitals and form a pi bond that regulates the interaction between the graphene layers. As we all know that the sigma bond is strong bond, as it is formed by head-to-head linear approach. So this is strong bond, and pi bond is relatively weak bond than sigma bond. So remaining fourth electron in the pz orbitals form pi bond. So this is arrangements of graphene as I discussed earlier. The figure 1a represents single layer structure of graphene. The dots show the carbon atom, adjacent carbon atoms. Then in figure B we will see Bernal stacked bilayer graphene stacking positions AA and V. Then in figure C trilayer graphene stacking positions which represent AAA, ABA and ABC, hexagonal, Bernal, rhombohedral. And in figure D we will see the sigma and pi bond which are connected with each other through sp2 hybridization in a honeycomb lattice. Moving on, next we will see that including all other allotropes of carbon like zero-dimensional fullerenes, one-dimensional carbon nanotubes (CNTs), and three-dimensional graphite, and also two-dimensionals. Graphene is most important of all. By upgrading graphene, all other allotropes can be obtained. So what are zero-dimensional materials? Zero-dimensional are those materials which have all of their dimensions in nanoscale. One-dimensional nanomaterials have only two-dimensional in nanoscale, and two-dimensional nanomaterials have only one-dimensional dimension in nanoscale. So graphene is strongest and thinnest because it is light, solid, and tough due to its remarkable properties like electrical conductivity. Next we will see graphene is most important of all. By upgrading graphene, we can obtain all the other allotropes. Among the nanomaterials, graphene is strongest and thinnest because it is solid, light, and tough due to remarkable property like electrical conductivity. Due to its electron are mobile. How its electron are mobile? Because graphene possesses a zero band gap. What is a band gap? Band gap means this is a property of a material where there is no threshold energy required to move electron from valence band to conductive band, which means that valence and conductive bands are overlapped with each other. Electron has no difficulty to move across the valence and conductive band. It can move freely anytime from valence to conductive band. So due to its electron mobility, graphene is not only limited to electrical and thermal conductivity, but there is a unique nanopores in graphene that are impermeable to gases, excellent chemical resistant, and have high surface area. Flexibility in surface Flexibility in surface chemistry and eco-friendly by using different catalytic substrate and metal films. Due to these unique properties, hydrocarbons gases like acetylene, ethylene, methane, ethane, liquids such as methanol, benzene, toluene, acetone, and solids like polystyrene, polymethyl methacrylate, PMMA, polyethylene glycol, and polyvinyl pyrrolidone. Carbohydrates are also used as a source of carbon in CVD. Next, we will see the mechanical properties of graphene. What are the mechanical properties of graphene, which include its Young modulus and also the fracture strength, which we will calculate it by which characterization technique is used to calculate this. So many group found that the mechanical properties of graphene with Young modulus and fracture strength. By using AFM atomic force microscopy, this is basically a characterization technique, we found that the Young modulus of few layers of graphene were found by force displacement method. Continuum elasticity theory also shows its mechanical behavior. 1.0 plus minus 0.1 TPa is a Young modulus of graphene by taking the thickness as 0.335 nanometers. The breaking strength of graphene is 40 Newton per meter. Through chemical reduction in graphene oxide, the elastic modulus of graphene is found to be 0.25 TPa. Remarkable hardness is found among macroscopic membranes. In monolayer graphene, the thermal and mechanical properties make them used in chemical sensors, and in composite material they are used as a fiber. Now we will see what are the frequencies of graphene. Frequencies of graphene lies in the range of megahertz were shown by nano electrochemical resonators manufactured from graphene nanosheets. Now we will see that graphene has a dense. Now we will moving towards its synthesis method. That how can we synthesize the graphene by various methods. Graphene has a densely packed, huge surface area due to van der Waals interaction forces, and therefore graphene layers tend to restack and reaggregate. Several attempts have been devoted to create techniques for synthesis to achieve high quality pristine graphene because of its planar hexagonal array and high aspect ratio. Mass level synthesis of graphene prevention of aggregation is a critical parameter. Finding a suitable and well-fitted fabrication method for mass-level graphene production and having defect-free graphene is the main objective. Generally, we will see that there are two approaches which we can use to make graphene. These are top-down methods and bottom-up methods. On the other hand, which method we will choose, it will depend on our end product, that which end product we will need, whether we need cost effective and whether it will be prepared by using low energy. So each method can be used depending on the end use requirements. The method are classified are presented in figure 2, which we will see in next slides. These methods may be mechanical exfoliation, chemical synthesis, chemical exfoliation, epitaxial growth, and chemical vapor deposition have been extensively studied. Other methods include arc discharge method, electrochemical exfoliation, microwave synthesis, gas-phase synthesis, total organic synthesis, solvothermal synthesis, unzipping of carbon nanotubes, and flash graphene synthesis. Top-down method is also called a destructive approach, which is the process of producing nano-sized graphene sheets with the help of graphite and its derivatives. So this is basically top-down method through which we can produce a nano-sized graphene sheets with the help of a graphite and its derivatives. Some of the top-down methods are to unzip carbon nanotubes, arc discharge method, liquid phase exfoliation method. These methods can be used to prepare monolayer graphene, bilayer graphene, and multilayer graphene. It will depend on our choice that which type of graphene we will want to prepare, whether it is monolayer, bilayer, or multilayer. Then we will choose method according to that. The graphene produced by this method is of superior quality, but it may also have some restrictions. The quality of graphene which is produced depend on the parent graphite. So there may be some limitations and yield can also be less. So there may be some restrictions of using this method. Yield can be less. So moving on to next, there is another method which is used to produce graphene. In this method, which take atomic size carbon as a starting material, this method is called construction technique or bottom-up approach. Some of the bottom-up method is total organic synthesis, substrate-free gas phase synthesis, and most common CVD, chemical vapor deposition method. This technique has some benefits than the top-down approach. Top-down approach produces a graphene having a large surface area. The bottom-up approach needs perfect technique during operation. This technique is expensive than the top-down method. So the bottom-up technique is basically expensive than the top-down method. The quality and amount of graphene developed depend on the method which we use to graphene. So as I discussed earlier, that it depends on us that which kind of graphene we will want to prepare. So the quality amount of graphene made will depend on our method, that which method we will use to prepare. Moving on next, this is basically a classification of graphene synthesis to basically two methods, top down and bottom up. Top down include mechanical exfoliation, liquid phase exfoliation, arc discharge method, and unzipping carbon nanotubes. On the other hand, bottom up method include chemical vapor deposition method, epitaxial growth, gas phase synthesis, organic synthesis, and others. So basically chemical vapor deposition include thermal chemical vapor deposition and plasma based chemical vapor deposition, which I will discuss in next slides. So this is basically classification of graphene synthesis. Now we will see, after the first report on graphene synthesis was published, 2 years later an experimental proof of thermal chemical vapor deposition method was given to synthesize a few layers of nanographene, with roughly 35 layers of graphene was made. Other method is CVD graphene by using substrate and hydrocarbon source. So the other method which is used to produce graphene take a substrate and hydrocarbon as a source. This may take place through a carbon diffusion in a metal substrate, which have high solubility in carbon, for example nickel, or by using metal surface adsorption with low solubility, for example low carbon solubility, for example copper. So it will depend. If we use nickel, it have high solubility in carbon, and if we use copper, it will have a low solubility in carbon. However, all different methods, CVD graphene is most useful to produce a monolayer graphene using large area of lives. CVD is also a cheap method which produce high quality graphene. Moving next, we will see to produce a monolayer for use in different devices. CVD is one of the most useful method. By exposing metal to different hydrocarbons at high temperature, large samples can be prepared. There are a variety of CVD methods available like thermal chemical vapor deposition, hot or cold wall chemical vapor deposition, or plasma enhanced chemical vapor deposition. The actual mechanism for the formation of graphene depends on the growth of substrate. It starts with the growth of carbon atom that nucleate on metal after hydrocarbons start decomposing and that nuclei develop into large domain. Liquid precursors can also be used like hexane or heptane. As I discussed earlier, there are variety of substrate as a precursors can be used. It may be liquid, solids. The transfer of graphene to material of interest can be difficult because graphene is inert. However, CVD is most complex and it demands high energy, but still one of the most successful methods to produce graphene by CVD method. So although this chemical vapor deposition is complex and also demands high energy for its processing, but this is one of the most successful methods through which nowadays we are producing graphene. Moving on to next, we will see that how can we prepare a functionalized graphene. So basically, why we do functionalization of a graphene? Functionalization of graphene can be basically done in many ways to enhance its response to analytical solution. So the basic purpose to do functionalization of a graphene is to, when we add this in analytical solution, it will show some response. So which methods we use to produce a functionalized graphenes are, which include to functionalize graphene are doping, defect engineering, and modification of surfaces. Through all these methods, we can prepare a functionalized graphene. Moving on next, we will now let's see the procedure of a chemical vapor deposition method. So what is chemical vapor deposition method? Chemical vapor deposition is a material processing technique that uses a chemical reaction to create thin films on a heated surface. In CVD, reactant gases are introduced into a chamber where they diffuse to a boundary layer and reach substrate surface. The gases then react with each other. The gases then react with heated substrate and form solid film. So hot gases are basically brought into chamber where the diffusion across the layer occur, and then they reach the substrate surface. Then they react with the heated substrate and form a solid film. Chemical vapor deposition method is most effective method to produce high quality graphene. To produce graphene, it requires high temperature about 1000 degrees Celsius, but CVD method is cheap. As I discussed earlier, that this process demands high energy, like temperature about 1000 degrees Celsius. But this is also a cheap method, so that we use it to prepare graphene. It uses limited material and synthesized graphene at low temperature like below than 600 degrees Celsius. High quality graphene has been produced on both metal substrate and insulating medium. Low temperature graphene growth by controlling thickness can also be done. So this was basically done by another method which we will discuss in plasma enhanced chemical vapor deposition. It uses a even lower temperature than chemical vapor deposition method. Chemical vapor deposition method is most commonly used method where thin films are formed through heated substrate through gas phase chemical reaction. As I said, that hot gases are introduced into chamber where they diffuse into a boundary and reach the substrate, and the gases then react with the heated substrate and where they form solid films. Moving on to next, we will see this is basically a setup, a furnace, a chamber of chemical vapor deposition, and there is also a gas inlet from where gases are introduced, and then they diffuse across a boundary layer and reach the substrate where they react and react with the heated substrate and form a solid film, and then unreacted gas move out from the gas outlet, and in center there is a metal foil. So this is basically a chamber of chemical vapor deposition method which is mostly used to prepare graphene. Although this demands high temperature, but this is cheap method, so we can use it to prepare graphene. Moving on, next we will see so how we will do CVD, how CVD is performed. In CVD method, gas species are brought into reactor where they travel to the hot zone. As temperature is highest, so there is hotness inside the zone. At the surface of metal substrate, hydrocarbon precursors break down into carbon radicals. So precursors which we introduce in the chamber, hydrocarbon precursors, they break down into radicals of carbon. These radicals of carbon then self-assemble to form graphene layer. In the course of the reaction, the metal substrate acts as a catalyst and affect the quality of graphene. In recent years, variety of transition metals such as iridium, platinum, cobalt, palladium, nickel, copper, these all have been used as a catalyst. So catalyst, basically, what is the purpose of catalyst? Catalysts increase the rate of the reaction, and catalyst is specific for specific reaction. So it will, through by using catalyst, we will not use the cost of catalyst because catalyst is mostly recovered at the end of chemical reaction, and catalyst increase the speed of reaction by decreasing the energy of activation. So these iridium, platinum, cobalt, palladium, nickel, and copper are used as a catalyst. The solubility of carbon in copper is 0.04% at 1000 degrees Celsius. The graphene growth happens via surface adsorption in copper due to low solubility, while surface segregation precipitation is main mechanism in metals such as nickel having higher solubility. Therefore, it is easier to obtain a monolayer graphene on a copper substrate. So it is more easier if we obtain a graphene monolayer on a copper substrate at 100 degrees Celsius because it is soluble in carbon. Next, we will see that various scientists have reported their work regarding chemical vapor deposition method which is used to produce graphene. So Wood reported growing mono to few layer graphene on a polycrystalline copper at 1000 degrees Celsius using methane as a carbon source precursor. The crystal quality and orientation of copper substrate greatly influence the quality of graphene growth. After CVD, Raman spectroscopy, this is also a kind of spectroscopic technique characterization, shows that having facets produce pristine monolayer graphene while copper surface prefer multi-layer graphene. Epitaxial growth of large area graphene on oriented copper single crystal is possible via chemical vapor deposition. Ishihara reported the synthesis of a single layer graphene on copper and found that the copper is optimal surface for defect-free graphene growth. The solubility of carbon in nickel is 2.03% at 1000 degrees Celsius and decreases with temperature. Since the formation of graphene on nickel is carbon segregation and precipitation technique, different cooling rates produces distinct segregation behaviors, affecting the thickness and the quality of graphene films. The atomically smooth surface in single crystal substrate enable the preferential growth of monolayer or bilayer graphene, while in a polycrystalline nickel substrate, multilayer were obtained. So these are basically techniques that how can we obtain monolayer if we want monolayer, if we want bilayer, and if we want multilayer. So these are various methods through which we can produce mono, bi, or multilayer graphenes. Moving on to next, now we will see that what defects which will produce and it will affect the performance of our graphene. Some of the major defects include wrinkles, folds, vacancies, line defects, additives, and impurities, all of which degrade the quality of graphene performance and affect its efficient applications for many purposes. Now, what the scientists have done to overcome this issue? To overcome this issue, Roff reported the synthesis of fold-free single-crystal graphene film on copper nickel with the dimensions of 4 cm into 7 cm. Bay also reported chemical vapor deposition growth of monolayer graphene on large flexible copper foils with dimensions as large as 30 inches that must be equal to 760 mm diagonally, which was then transferred to the target using the R2R method. The graphene sheet's resistance was as low as 125 with 97.4% optical transmittance. Moving on to next, we will see the setup of chemical vapor deposition. The figure 4a shows chemical vapor deposition furnace system. So this is basically the furnace of CVD. Figure B shows the Raman spectra and mapping produced graphene. This is a Raman spectra of graphene and also the mapping which is produced. Figure C shows roll-to-roll CVD apparatus in which there are quart tubes, and inside the quart tubes there are antenna. Beneath his sample stage and sides are winder and unwinders. And figure D represents Raman spectra and figure E represents transmittance of transferred graphene films. So this all is basically a CVD furnace system and its Raman spectra and transmittance transferred graphene films which we obtain. Moving next, we will see that what is basically plasma chemical vapor deposition method. Plasma is basically the fourth state of matter, and what is plasma enhanced chemical vapor deposition method is a chemical vapor deposition process used to deposit thin films from a gas state to solid state on a substrate. Chemical reactions are involved in the process which occur after creation of plasma of reacting gases. The plasma is generally created by radio frequency, alternating current frequency, or direct current discharge between two electrodes, the spacing between which is filled with the reacting gases. So what is plasma chemical vapor deposition method? By using this method, we can produce graphene at even low temperature, and optical transmittance produced by this method also increases by using the plasma enhanced chemical vapor deposition method. The approaches to growing high quality graphene films on a transition metal substrates are dominated by high temperature thermal chemical vapor deposition method. A low temperature process for graphene synthesis would be required for its application in electronic devices, and plasma chemical vapor deposition could be excellent alternative to thermal chemical vapor deposition method. So we will see that thermal chemical vapor deposition require high temperature. So graphene produced by that method must be limited to use in applications like in electronic devices. So for using that way, we produce graphene through plasma chemical vapor deposition. So this is an excellent alternative to thermal CVD. The formation of plasma from the reacting gas precursors enable thermal chemical vapor deposition at a lower temperature. So we produce graphene through lower temperature by using plasma chemical vapor deposition method. Kim decreased the synthesis temperature to 450 degrees Celsius and reported graphene on a nickel foil with a high transparency of 89%. Yamada also used microwave plasma chemical vapor deposition to create 294 mm wide FLG films on a copper substrate at 400 degrees Celsius with 95% optical transmittance. With the lowest synthesis temperature of 317 degrees Celsius, graphene layers having optical transmittance in the range of 78 to 95% have been achieved. So as we see that by decreasing the temperature 450 to 400, then 317, the optical transmittancy ranges has also been increased, and graphene of good quality was produced, which we use them in very many applications to that place where we not use the graphene which is produced by thermal chemical vapor deposition method. Now we will move toward the applications of CVD graphene. That what are the applications of chemical vapor deposition method graphene? So in first stage transistors and transparent displays, the use of graphene in the field effect transistors FETs is one of the promising application of this material. So what is basically a transistors? Transistors are basically used in electronic devices like in computer, cell phone and in robotic systems. Since graphene is conductive material, it cannot be utilized directly in transistors applications. However, graphene in the form of nanoribbons act as a semiconductor. This means that it can exhibit a band gap and can be turned on and off and thus can be crucial component of nanotransistors. By patterning graphene into GNRs, the band gap can be engineered to have values up to 400 volts. There are various methods for fabricating GNRs for field effect transistors applications including chemical and lithographic methods. GNRs with widths ranging from 20 to 30 nanometer have been created using lithographic patterning. However, recent study by Linnaeus reported the fabrication of GNR of only 0.95 nanometer in width and with the high current on to off ratio that is 105. Wu reported the synthesis of sidewall transistors with the smallest gate length of 0.34 nanometer and up to 1.02 10 raised to power 5 on and off ratio. The sidewall transistors were fabricated using chemical vapor deposition with graphene and molybdenum disulfide to achieve devices below 1 nanometer. The mobility of graphene field effect transistors depends on the choice of substrate materials. In this context, Alum created a graphene-based ferroelectric field effect transistors having a mobility 4.2 into 10 is to power 4 and about on and off ratio. This is basically in figure 5a and b. We will see the STM image of synthesized GNR on gold and schematic of graphene nanoribbon field effect transistors. In figure 5D, we see device configuration of graphene transparent conductive electrodes and optical transmittance comparison between indium tin oxide and graphene. We will now discuss the indium tin oxide and how it is replacing graphene nowadays. So this is basically the optical transmittance comparison which have been done between indium tin oxide and graphene. Moving on to next, we will see that indium tin oxide ITO is a transparent conductive material used in smartphones, television screens, and many other touchscreen applications. However, the limited availability of indium is a growing concern in ITO market. It is anticipated that graphene will be one of the materials that will be in highest demand for the development of future optoelectronics. So as indium tin oxide is not available in the market, it has its limited availability. So this is concern for the ITO market. So graphene will now replace ITO and it has highest demand for the development in future optoelectrical devices. Moving on next, we will see second application of CVD graphene in coatings. How can we use graphene as a coating? Silver films are extensively used as optical coatings. However, silver is expensive and unstable in air and prone to oxidation. Although common protective coating have ability to stop corrosion of silver, but it might changes its optical properties. If we do silver coating, it might stop corrosion, but it will change its optical properties. When compared to bare silver, the rate of corrosion of silver films covered with graphene was reduced by 66 times. So if we cover with graphene, so the rate of corrosion was reduced. Prosai found that the graphene covered copper exhibited a corrosion rate 7 times lower than that of bare copper in sodium sulfate solution. Similarly, in case of nickel covered with graphene, an enhancement in the corrosion resistance by 20 times was obtained. Graphene and its derivatives are also widely used as a reinforcement in the coatings to improve wear resistance. The titanium alloy mixture has a relative wear resistance of 1, and with an optimum graphene content of 3 grams per liter, the resistance is increased to 12.2. Graphene modified aluminum trioxide, titanium dioxide coating have a 20-25% lower wear rate than non-graphene coatings. Zhou also observed an improvement in the wear resistance of micro-arc oxidation (MAO) coating prepared on tin 6 aluminum 4-volt alloy with graphene oxides. They found that the MAO coating with 10 graphene oxide had comparatively superior tribocorrosion resistance with fewer micro cracks but a smoother worn surface than that of 5 and 15 graphene oxide coatings. On number 3, we will see application of CVT graphene in biomedicine. How we use CVT graphene in a biomedicine. Graphene has a vast application in biomedicine. To use in photothermal therapy and imaging, nanographene has been developed. The sensing power of graphene can be used in chemistry of graphitic materials such as in detection of biomolecules, microbial cells, and organic molecules. Nanographene provide high surface area which effectively bind to biomolecules. It can be used in a gene and drug delivery as a carrier. So there are varieties through which we can use graphene in a biomedicine. Figure 5 shows the uses of graphene in biomedicine. Like sensing applications may be biological, organic, or gases. Then sensor device graphene tunability may be nanoparticles, DNA based antibodies, or organic molecules. Moving next, we will see application of graphene in electrochemical sensors. Graphene is also used in electrochemical sensors because it transfers electron at a faster rate and has high redox potential with cathode and anode have made graphene and its oxidized form graphene oxide both are used in electrochemical sensors. So why graphene used in electrochemical sensors? Because it has high redox potential and transfer electron at a faster rate. Due to advancement made in graphene with various methods like polymerization, doping, different electrochemical sensors were made. To increase electrical conductivity and surface area by changing the structure and shape, which should increase its way of working, electrochemical sensors has many applications in many things like in wearable electronics and in vivo analysis. Electrochemical sensors has many benefits like they are highly sensitive so that they are using LOQs and LODs. Moreover, they give response immediately so that they are used in alarm-based systems because they are simple so that they are used in many geometries configuration and also in electrode material. Moreover, they also have a benefit of low cost of material and equipment which make them used for various purposes. Moving on next, we will see how CVT graphene is used in anti-cancer therapy. Graphene-based materials are nowadays used in many compounds like in anti-cancer drugs, proteins, carbohydrates, and polymers. To increase the transport of tumor cells, graphene-based derived compounds are modified. To find presence of cancer in the body, graphene is also used to detect it. Oxides of graphene stops the growth of tumor in ovaries, breast, lungs, and in pancreatic region. So when we use graphene oxides, it stops the growth of tumors in various parts of the body. They are more dangerous for cancerous cells other than for non-cancerous cells. To use graphene-based materials for the treatment of cancerous cells is still in the process of completion. There are many hurdles in this way. To understand the impact of graphene not only to cancerous cells but also healthy cells must be studied. In respect of its method, that means how it impact is very important. Graphene-based materials are harmful may be inside or outside of the body. Moving next, we will see application of graphene in agriculture and wastewater management. As we all know that nowadays our water and agriculture systems are on the are very polluted due to various kinds of waste which we produce, and to maintain sustainable environment it is very difficult task nowadays because water is contaminated with many harmful substances which rise from maybe organic or inorganic sources, both sources, which are released from industry, household debris and agriculture. All these are present at an alarming rate. To large amount of water contamination, aquatic animals are on the edge of extinction. It is very difficult to find clean water for using purpose. However, more than 70% of Earth's surface is covered in water. So it is very difficult to find clean water. Even our Earth's surface, more than 70% is covered with water. There are many methods which are used to remove water pollution, and at present we are mostly using to remove different kind of pollutants from water nanoporous membranes, which are mostly made up of graphene. For gaseous liquid material, these nanomembranes act as a barrier. So nowadays, to remove pollutants from water, we will use a nanoporous kinds of membranes which are produced from graphene. So in this way, graphene will provide benefit to remove pollutants from water to clean our agriculture and wastewater management. Moving next, we will see uses of graphene in industry. That how we will use graphene at a sports level. Graphene commercialization is fastly moving from laboratory to market. This trend will increase in coming years. For example, graphene is used in sports industry to produce tennis, helmets, various other products. By mixing graphene and thermal benefits of graphene, an Italian-made motorcycle helmet was launched in October 2016 with a collaboration of Italian Institute of Technology. To increase heat dissipation and to provide more comfort, graphene is used as a coating to outer side of the helmet. Graphene can also increase the speed and stability of tennis racket. Graphene can also increase energy distribution and improve weight of a tennis racket. A British sportswear manufacturer, Innov8, has launched a series of graphene-added hiking boots and shoes as well. By using the fiber of graphene in textile, it will provide anti-static and antibacterial clothing that will keep heat and block harmful ultraviolet radiations. So by using graphene as a coating, we can produce strong helmet, can also increase the speed and stability of tennis racket, and also improve the weight of tennis racket. And various sports manufacturer has adding graphene to their products. And by using, if we use the fiber of graphene in a textile, it will keep the heat and also block harmful radiations entering to body. Next we will see application of CVT graphene in batteries and supercapacitors. What is a battery? A machine which is convert chemical energy into electrical energy is called a battery. It is very smooth thing for use in daily life. Due to high energy density, lithium-based batteries are used in energy storage system. In lithium-ion batteries, due to high energy density, degradation in cathode is dendritic structure. Ten shows the formation of lithium dendrites can be induced on graphene by coating of porous silicon oxide. Lithium-sulfur battery is a rechargeable battery. It involves graphene coating in it. Ink-based graphene is also used in printing and in electronic devices. Gore used graphene aerosols ink to print micro supercapacitor. Yun made a durable supercapacitor by developing graphene ink. Supercapacitor is a remarkable device used in various sensors. Supercapacitors are used in electric ways of transportation, which means that they have benefit of fast charging. There are many types of supercapacitor depend on their way of use. One type is supercapacitor that store energy as electric double layer, and other is pseudocapacitor which store energy by redox reaction. So there are basically main two types of supercapacitor. One is that store energy by redox reaction, which is a pseudo capacitor. Other is that store energy by electric double layer. Moving next, we will see application of CVG graphene in energy storage devices. This is basically linked to capacitors and supercapacitor and batteries. Due to high surface area of graphene, it is used in energy storage devices such as supercapacitors and batteries. It is used in lithium-ion batteries where graphene acts as anode and possesses 1000 mA higher capacity than graphite electrode. Graphene also provides fast charging and long-lasting batteries in few seconds. So this is the benefit that graphene has a long-lasting battery and super fast charging. It is also used in solid-state supercapacitor due to its flexibility. With increasing amount of graphene, it will give high capacity in supercapacitor. Wang made pillared graphene by using hydrogen gas and ethylene as a carbon source by chemical vapor deposition method. The synthesized graphene is used in lithium-ion battery as an anode and making it stable for more than 250 cycles. Supercapacitor has many benefits. Now we'll see the benefits of supercapacitor, like it runs for a long time, it has high power capacity, have a fast charging ability. Supercapacitors have ability to take the place of batteries which are rechargeable because supercapacitors have energy storage properties. Supercapacitors have low energy density as compared to lithium-ion batteries. So these are the benefits of supercapacitor. Moving next, we will see application of CVG graphene in automobiles, marine and aerospace industry. In present time, there is focus to produce lightweight but strong things which are used for multiple applications, like we use them in marine industry, automobiles or aerospace industry. This eliminates the weight of parts and reduces the amount of fuel required, which results in decrease the cost of fuel and consumption of fuel. This will also help to improve climate because it will reduce the emission of carbon dioxide, and it will also help to improve the environmental pollution. As we know that today a lot of fossil fuel burns and carbon dioxide is released into atmosphere, it will increase the amount of carbon dioxide and cause global warming. So by using this, we will also help to improve global warming and improve our environmental pollution. Due to excellent strength and hardness, heavy materials which are made up of steel are replaced with fiber reinforced composite materials. Many types of high strength materials are used as a carbon fiber, glass fiber are used in textile. Thermosetting polymer resins are used mostly because they are thermodynamically stable and chemically inert and have a good mechanical properties. Also, thermosetting polymers can undergo cracks. To remove all these problems, graphene-based nanomaterials are used nowadays in FPCs, which shows a huge improvement in plane and out-of-plane properties. They possess high mechanical properties and have a high strength to weight ratio. So by using graphene in automobiles, marine, and aerospace industry, we will try to improve strength and make them lightweight and also reduce the amount of fuel which required, which will also help to decrease the cost. Moving on, next we will see that a motor company, which is basically a Ford motor company, had put back its parts which make more noise with parts made up of graphene like chain driven gears, pumps, fuel rail and belt driven pulleys, which are located on the front engine. BMW is one of the examples. Many graphene based materials is used in aquatic components because they protect them from corrosion and can give them a better life. Various parts of ships like spars, keels, masts, rudder, hull, tip, till and poles are made up of graphene based polymer composites. Graphene-based material with its captivating structural properties and conductive strength with its many practical applications are also used in aerospace industry. Now, how we use them in aerospace industry? In different parts of aerospace industry, like in panels, ribs of aircraft wings, fuselages, fuel tank and tail assemblies, graphene-based polymer composites are used because of its toughness and strength. So, due to strengthness and toughness of graphene, It is also used in aerospace industry, automobiles industry, and also in marine industry. Next, we will see about more than 50% parts of Airbus's aircrafts are made up of many composites with enhanced mechanical strength, as it can bear tolerance, thermally stable, and can tolerate corrosion. For making many different type parts of helicopter with multi-scale composites are used. These helicopter parts include interior parts, sails, propellers, fan blade, and rotating blades. Fiber-based composites are used due to enhanced properties, but cost must be reduced for their applications. More research is needed to reduce cost. So research is likely to continue on how we will reduce cost. Next, we see the application of CVD graphene in solar cells. So solar energy, one of the most energy used nowadays, as global warming is a very strong issue which the whole world is facing nowadays. So by shifting from non-renewable sources to renewable sources, it will also help to reduce the combustion of fossil fuels, which will decrease the emission of gases in atmosphere, and it will also help to improve global warming. Solar energy is one of the most used form of renewable energy on our planet Earth. Planet Earth receives 3 into 10 to power 24 of the solar radiation from Sun per year. This data is 10,000 times the whole universe now consumes electricity. Solar energy is very useful source which gives security. Energy research is in the process to produce solar cells and photovoltaic, which may help to reduce the cost of electricity and find a good method to improve efficiency. Currently, the solar market uses a crystalline silicon, which is well-maintained technology. Various researchers show that solar cells which are silicon-based, which have efficiency of 26%, which is near to the theoretical limit of 29.1%. The main demerit of this method is its high cost. So by using silicon, it will cost high. Other method is PV photovoltaic films, which is used in this technology such as CDTE. Due to remarkable properties of graphene, which means that it has a potential to reduce cost and increase efficiency. So we use graphene here because we will know that it is cheap and also increase efficiency. The properties of graphene, like its mobility of electron, conductivity, power, flexibility, and its physical and chemical stability, it is why that graphene is now most reliable material which we are using in our solar cells. Next, we will see the graphene-based application in surface coatings. Graphene-based surface coatings are enormously used in biomedical devices. The method of coating depends on substrate material, and it may be metal, a polymer, or its structure depend on how coating is applied. Through electrophoretic deposition, graphene nanowalls are coated on stainless steel as it has a strong antimicrobial activity, both in case of gram-positive and gram-negative bacterial cell. Due to direct contact with the sharp edges of nanowalls, bacterial cell wall may be damaged. So this is how graphene are used in surface-based coatings. Next, we will see the application of graphene in a wearable technology, how we will use graphene in a wearable technology. In wearable technology, material based on graphene are widely used. Graphene can show its performance in every field due to its remarkable properties like electrical conductivity and various other mechanical properties. In electronic heaters and biomimetic gas sensors, graphene quartz fiber GQF are widely used for industrial applications. The use of gas sensors is mainly done for two purposes. One is to screen the air quality, and other is to detect the presence of many toxic gases like methanol, ethanol, ethylene, formaldehyde, carbon dioxide, and acetone. Moreover, they can also be used in textile as they are preferably more washed as compared to solid-state gas sensors. With graphene-based gas sensors, different kind of humidity and volatile organic compounds can be detected. This can be used to detect harmful material present in atmosphere like organic vapors, harmful gases, and other chemical agents. Moreover, by using wearable devices, Human body temperature, heartbeat, blood pressure should also be measured. When human body or environment causes change in conductivity, it will also give results. Now last application in many other fields, like with many different properties, types of properties, strong cost efficient and lightweight sports material are made from graphene based composite. At present, many types of sport items like sticks, helmets, tennis racket, bicycles frame and golf clubs are made from different variety of graphene based nanocomposites. In military defense system, graphene based materials are also used, and nanocomposite materials, a huge variety of nanocomposite materials are used in this industry. Manufacturers of graphene composite materials like high strength, large strength to weight ratio has enabled graphene to use in different kind of military automotive parts. In military automotive parts, graphene is used because of its high strength and strength to weight ratio. Next we will see conclusion. Next we will move toward the conclusion and what is the future prospect of graphene. Several different features of graphene, including chemical stability, high surface area, electrical and thermal conductivity, flexibility by bringing down it to nanoscale, to use for numerous various applications. This presentation shows advanced synthesis of graphene and its applications. Various methods are successfully developed which shows high performance of graphene and high quality of graphene. It includes various methods like CVD and by unzipping of carbon nanotubes and various other methods. With good conductivity and zero defect, it produces high quality sheets of graphene. It must be noticed that quality of graphene produced depend on process and parameters used during CVD. Exfoliation technique is used for the industrial scale manufacturing which give more than 50% yield. It is also used to detect various diseases like malaria, COVID-19. It is also used as a sensor in medical devices due to its high sensitivity. To prevent corrosion and to make metal oxidation resistance, graphene is used as a protective coating. Graphene is also used in energy storage devices as electrode due to its non-flammable nature, surface area, such as in lithium batteries. The use of graphene improves its performance. Composite graphene is also used in thermoplastic thermosetting polymers. These processes are cheap, eco-friendly and environment and also facilitate graphene-based productions at large scale. The fabricated graphene has vast application due to its good mechanical properties. Some of the graphene-based material is used in their solar cells, medical equipment, sport items and also automobile parts, automobile frames. Graphene based materials are used in water purification and wastewater treatment. Furthermore, graphene based materials are used in nanocomposite industry. Nowadays graphene is used in industry, but scientists are still trying to study to discover more and more. Graphene is also used in drug delivery and also in biomedical equipments. Graphene material is also used to increase the biocompatibility, to remove toxic elements, to protect the environment. So at last, the quality of graphene also depends on which reagent we will use. Graphene has applications in all the areas of life in terms of its practical application. As I discussed earlier, that it depends on our end use, that which method we use from which we are preparing graphene. Graphene has an application in all the areas of life in terms of its practical application because it is flexible enough to mobility. It is used in transparent displays. Apart from all these, future research on graphene include to produce a reduction process that is eco-friendly, that can show high electrical conductivity and good mechanical properties. So in a nutshell, graphene is an amazing material in the world that can be polished in many ways to use in a different application areas. So that's all from my today's topic. Thank you so much.